Hi everyone, in this video I'm going to summarize this paper titled Ambient Synchrophasor Database Power System Inertia Estimation Using System Identification Method, so that by the end you will understand exactly what this research is about without having to read the full paper yourself. Let's start with the abstract. As renewable energy sources like wind and solar replace traditional generators, power systems are losing their natural inertia, and that makes grids less stable. This paper proposes a system identification-based method that uses ambient data to estimate this inertia in real time and tests it on a simulated two-area power system. Now let's look at how the system itself is set up. Here is the two-area test system. Area 1 has a thermal plant and a solar farm. Area 2 has a thermal plant and a wind farm, and both areas are connected by a tie line. Each area also includes a virtual inertia unit and an energy storage system, which emulate the inertia that renewables normally lack. With the system defined, let's move to the proposed method itself. This flowchart shows the three main steps. First, pre-processing the PMU signals, handling missing data, removing the main, and filtering. Second, state space system identification. And third, extracting the inertia value from the identified model. Now let's see the mathematical structure behind state 2. This is the state space representation the model is built on. Inputs, states, and outputs connected through matrices A, B, C, and D. The inputs and outputs are measurable, but the states are unknown and get estimated through the subspace identification algorithm. Let's see how this maps onto the full dynamic model. This is the complete dynamic model of the interconnected system, including the governor turbine, virtual inertia loop, and the LFC secondary control for both areas. And here in table 1 are all the parameters used: inertia constants of 5 seconds for area 1 and 4 seconds for area 2, along with the governor and turbine time constants. These numbers are our reference values for later comparison. Now let's look at the simulated disturbances. Over a 600-second simulation, the loads and renewable sources fluctuate randomly. This is what creates the ambient excitation the method relies on, instead of needing a large disturbance event. With this data generated, let's check how well identified model performs. Here is the cross-validation. Even though the real system has an order of 14, the identified model only needs an order of 5, and as you can see, the estimated frequency response still closely matches the actual one. That confirms the reduced order model is reliable. Now the key question: how accurate is the actual inertial estimation? This table gives the answer. For area 1, the real inertia is 5 seconds and the estimated value is 5.0179, an error of just 0.358%. For area 2, the real value is 4 seconds versus an estimated 4.0051, with an error of only 0.1275%. Extremely accurate results. Finally, let's see how this performs when inertia actually changes over time. This is the online tracking result over 400 seconds. Notice around 40 seconds, the inertia of area 1 is deliberately dropped to 3 seconds and then restored to 5 at 60 seconds, and the method tracks this change closely in real time, proving it can follow dynamic inertia variations, not just estimate a fixed value. So to sum up, this paper introduces a subspace-based system identification method that can estimate regional power system inertia in real time using only ambient PMU data with very high accuracy, even as renewable penetration increases. Stay with me. In the next video, I'll walk you through some related papers in the same research area.